pretty much everything Jacob said, ditto. So we're going to start off with everything he said about what you can measure about stars, you can measure about galaxies. But I started out with a bunch of the what's going to be on the test lines. So if you want to know what's going to be on the test, just read this and then you're done. You can walk out. You know all the answers. So you live in a galaxy, and so if my job is to explain to you what those are, I love this quote. I found it in a textbook about 15 years ago, and I think it's probably the best way to summarize Astro 101, what are stars and what are galaxies. So the star is the basic unit of the galaxy, right? So galaxies are made up of about 100 billion stars. And then the galaxy is the basic unit of the universe. So there's about 100 billion galaxies in the universe. So if you say, well, what is the universe? It's made up of galaxies. And then if you say, well, what is a galaxy? It's made up of stars. So the end, we're done. But I'll keep going from there. So one of the things we found from years and years and years of working on Intro Astro and seeing 15 weeks later how much people remember, there's a lot of confusion about where you live. Like, what's the difference between the solar system and the Milky Way galaxy? So you do live in a solar system. You live in the solar system. You live on the Earth, and the Earth is orbiting a star, the sun. But the sun, right, a star is just a basic unit of the galaxy. So you do also live in the Milky Way galaxy. Our solar system is just one star and one set of planets orbiting around inside the Milky Way. There's about 100 billion others alongside our own solar system. I'm going to talk a lot about size and scale, how big are things in the universe. So if you're ever, thinking about what's the difference between the solar system, what's the difference between that and the Milky Way, the answer there is, again, a big number, about 100 million. If you think about Pluto as being really, really far away from you right now, and if maybe you learned when you were very young that wow, Pluto's really far away, it's the edge of the solar system. Well, if you think about that distance between us and Pluto right now, if you lay 100 million solar systems edge to edge, that would cover about the size of the Milky Way galaxy. So our galaxy is about 100 million times larger than our solar system. All right, so again, if you want to know what's going to be on the test and you just want to know, cut to the chase, what's the answer? What I really want to talk about for the rest of my time talking about galaxies is I want to focus a lot, again, like Jacob did about stars. Well, how do we study them? So you live in a galaxy that's surrounded by about a dozen or so other small galaxies. Right, galaxies are just made up of stars. They're filled with lots and lots and lots of stars. So the nearest galaxies, including the one that you're inside of, we don't really study them as a galaxy. We study them as collections of stars. So the nearest galaxies we study by studying what we call their stellar populations. Then if you say, okay, well, let's go a little bit further out. So inside what we call the local universe, there's lots and lots and lots of galaxies. That's where we can sort of make out these pretty pictures of the galaxies, and we can see what their structure looks like. So within about the nearest few 100 million light years or so, that's where we do study galaxies as a whole galaxy, and we look at individual pieces of them. But here's the fun thing that Jacob showed you. The very first thing he showed you was, here's a picture of all of these points of light. And he said, all of those little pinpoints of light are stars. Well, here's one little thing I want to change on him. Some of those very little pinpoints of light are, in fact, galaxies. If you take a giant galaxy made up of 100 billion stars and you put it so very far away from us that you can't make out any detail, it will appear so small to even the biggest telescope that it will look like a pinpoint of light as well. And when you start pointing your gigantic telescopes at the sky and taking pictures of these many, 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 many stars, in fact, some of them are not stars. They're just galaxies that are really, really far away. All right, so here is a beautiful, gorgeous picture of a place that's a little bit darker than it is here. The reason I know it's a little bit darker than it is here is because you can't see that when you go outside here, unfortunately. If you go to Black Moshannon State Park, you go to Cherry Springs State Park, if you go to Cherry Springs State Park, you will see a night sky that looks like that, and you'll see this gorgeous band of the Milky Way. So that's our galaxy, right? But not only is that band our galaxy, every single one of those stars that you see in that picture is our galaxy too, because you live inside that Milky Way. So every star that you can see in the sky is just one star in our Milky Way. So here's a beautiful cartoon. You've probably seen pictures of the Milky Way. I'm going to show you an artist's picture of the Milky Way in just a few moments. But our galaxy is a little bit more complicated than you might ever really thought. You've probably seen these pictures that have the beautiful spiral arms, and maybe someone has told you once upon a time that our galaxy is a flat disk galaxy, but that's not all there is to the Milky Way. Yes, there is a flat disk part of the galaxy, but there's also these bunch of star clusters that orbit up above that disk of the galaxy, and there's some other ones that orbit down below the galaxy. So in fact, there's actually a really, really huge spherical region that encloses that disk part of the galaxy, and that spherical region we call the halo of our Milky Way galaxy. So if you want a picture in your head, what is the Milky Way? This is, to me, the sort of best picture to have in your head. There's a sort of fatter region in the center that we call the galactic bulge. There's a flat part that we call the galactic disk, and then there's a spherical part that we call the galactic halo that all the rest of that stuff is contained inside of. So here's the sort of more the more common depiction of what our Milky Way galaxy looks like. And a lot of times we get asked, is that really what the Milky Way looks like? And the answer is kind of, sort of, maybe. And the reason I can't say that's exactly what our Milky Way looks like is because, again, you're inside of it. So we do the very best that we can, being stuck here on Earth, taking measurements in every direction we can see and trying to piece that together into a map of our Milky Way. But the only way we could get a picture of our own Milky Way is if we could, again, grab the Enterprise, go at warp 5, warp 10. If we could get, many, many millions of light years up above our galaxy, then we could take a picture of it, but we can't do that. That's where you are right now. And the very furthest thing that we've ever launched away from the Earth, the satellite, one of the satellites of the 2 Voyagers, it's been going for decades, and it's less than a pixel away from the center there that's called the sun. So we have not, there's no way for us to get far enough outside of the Milky Way to then turn around and look back and take a picture. So this is just an artist's impression of what we think the Milky Way might look like. All right, so this is a really fun story to tell. So around 100-ish years ago, a little bit less than 100 years ago, we didn't know, was our Milky Way the only galaxy in the whole universe? In fact, what's the difference between the galaxy and the universe? 100 or so years ago, the answer was, we're not sure. We think, maybe the Milky Way fills up most of the observable universe. But if you had a really good telescope and you had a really good camera, you could take pictures of things that looked like this. And so people at the time, astronomers at the time, said, well, what are those things? And if you go grab a textbook from 100 years ago, and if you don't happen to have a 100-year-old astronomy textbook, I have one at my house, so you're welcome to come read it. But this was called the Great Nebula in Andromeda, right? So nebula just means cloud of gas. And so the question is this thing just a cloud of gas inside the Milky Way? Or is it another Milky Way? And we didn't know the answer. So does anybody know who figured it out? Yeah, right? So if you're talking about galaxies, the answer to who figured it out can often be Edwin Hubble. Of course, there were lots and lots of other people who contributed, but the person we give credit to is Edwin Hubble. So you look at this picture and you say, well, there's lots and lots of stars in this picture. But if that's just a cloud of gas inside the Milky Way, maybe all those pinpoints of light are just stars in the Milky Way. And so maybe this is a cloud of gas inside the Milky Way. Well, Hubble took a very famous picture of this in 1923, and he measured the distance to one of the little pinpoints of light in here. And the answer came out to be that pinpoint of light was outside what had been measured to be the edges of the Milky Way galaxy. So this was the very first thing we figured out wasn't inside the Milky Way. And so I like to try and think a little bit about what that time period was like. You know, before that discovery, sure, there were arguments, but a lot of the textbooks talked about, you know, the Milky Way being the only galaxy in the universe. And suddenly, you know, in a matter of just a few years, it was like, well, no, the Milky Way is just one of many, many galaxies, and all of these spiral gas clouds are not spiral gas clouds, but they're other Milky Ways out there in the universe. So these things are gorgeous, and I'm going to show you some pictures of some of these really beautiful galaxies, but I'm going to, in particular, show you pictures of some of the nearest ones to us. And what took Edwin Hubble, the very largest telescope and the very best camera that was in use at the time, was barely able to make this measurement to show that this was a star inside this other galaxy. Now it's routine. You can go out, grab maybe $100,000 or so telescope, but you can grab a telescope, get a digital camera, you can take an image, and you can start resolving these nearby galaxies into stars. So it's pretty routine for us to measure individual stars in some of these galaxies anymore. So, but even though we can discern individual stars in these other objects, we can also study them as, we can study all of the faint light from those objects and study millions of stars all at once. So for example, here's a galaxy, and this is one of the two Magellanic Clouds. So you can, if you've ever been south of the equator, you can just go outside at night and look up and see these in the sky. They're bright enough to be seen with the naked eye. So these are the two closest somewhat large galaxies to us, and this one is pretty easy to resolve into stars. And if you do that, you can measure how far away it is, and the answer to this is about roughly 150,000 light years. But besides studying individual stars, you can take a spectrum, or you can take a picture of that area, and you can measure the light that's coming from that area, and we can tell that that's a cluster where new stars have been born, and there's a very young group of stars in that particular spot right there. So here's a picture of M81, another one of the nearby galaxies that's relatively easy to image with a small telescope. And now this one is now far enough away, several million light years, that it's not obvious that this breaks up into stars. But this area in here is the bulge of this galaxy. And in fact, the light that you're seeing, that sort of pale yellow glow, is the glow from somewhere in the neighborhood of tens of billions of faint stars that all, when you add up all that light, you get that glow. So we can, with the Hubble Space Telescope, we can resolve that into stars, and we can measure the light from individual stars in this galaxy. But it's more common to study all of the light coming from this area of the galaxy and try to tell the properties of in general, all of the stars that make up that part of the galaxy. So you probably noticed, so Jacob really did a great job of setting up everything I was going to say. He went to all this trouble to explain to you, well, some stars are blue and some stars are red. And so when you look here, here's a part of the galaxy that's all kind of a pale yellow. And that's because almost every single one of the stars in that part of the galaxy are very cool. And then here you have these other parts of the galaxy where you can, to your eye, you can just see that glowing a bright blue. And it turns out it's not because all of the stars in that area of the galaxy are really a bright blue, but the most luminous ones, the ones that give off most of the light, are blue. And so their light just swamps out all of the light from the paler yellow and orange stars that are found in the same part of the sky. So here's M87. So M81 is a lot like our own Milky Way galaxy. It's a spiral galaxy. You can see those spiral arms. M87 is an elliptical galaxy. I know there's a couple of astronomers in the audience, and if you study elliptical galaxies, I'm going to apologize up front. But my line about elliptical galaxies, like, these spiral galaxies are beautiful, and every one is unique. I mean, we do categorize them, but every single one of these spiral galaxies really stands out as having some properties that make it stand out from the others. And then I say, well, if you've seen one elliptical galaxy, you've seen them all. It's a ball of stars. They're all the same color. It's a ball of orange. So there are 100 billion-ish, probably more like 200 billion stars or 300 billion stars. But they're all kind of cool stars, so there's really no structure. Now, that being said, M87, to be perfectly fair, it does have this cool little jet of light being shot out there. So maybe M87 is at least a little bit unique compared to the others. So here's a favorite of a lot of folks who like to look at galaxies. This is called the Sombrero Galaxy. We're seeing this one edge on. So this is the edge of that flat disk. And what makes this galaxy different than our own is if you were seeing the Milky Way from the edge on, the bulge of the Milky Way would be not quite as extensive and not quite as large in that direction. So this galaxy is really dominated by that bulge population. And you can see, you don't really see a ton of blue light in here. You see a lot more orange light because the central part of this galaxy is so large. All right, so ultimately, here's another thing we attribute to Edwin Hubble. So when we were figuring out that these objects were not clouds of gas contained in the Milky Way, but that they really were their own type of galaxies, we found, well, some of them had wide open arms, some of them had kind of wide open arms, but had like a straight bar through the center. Some of them just looked like balls of stars. So Hubble came up with this, what's called the tuning fork, that you have these elliptical galaxies that seem to get more progressively elliptical. And then you have what's called an S0 that kind of sort of looks like a spiral, but maybe more like an elliptical. And then you have spiral galaxies with the arms rather sometimes open, sometimes not, sometimes with a bar, sometimes not. And so he was trying to infer, just like Jacob showed you with the HR diagram, here's sort of a diagram categorizing all these galaxies. Can we use this really to understand galaxies? And it turns out not quite as much as Hubble hoped. So this is like the textbook version of this, but I love showing this picture because this is now real galaxies that show you the diversity of properties, right? And so the things that we call SCs would be over here, and SBs would be over here, and SAs, and then here are the barred spirals, and then here are the ones that are kind of in the middle. Here you've got some ellipticals, and then here you've got the ones that are just a mess, irregular galaxies. So it turns out, trying to trying to classify these into some, but ultimately we can say that every single one of these is just a gigantic city of stars, and its properties are really just made up of the properties of adding together the light from about 100 billion or so stars. All right, so here's what the last thing I wanted to say about galaxies. I like to think, and most astronomers tend to think about galaxies in sort of three bins. There's the Milky Way and the nearest galaxies to us, where they're so close to us we can really think of them as big giant groups of stars, and we can study individual stars in them. And then you get a little bit further away, and sure, we can still kind of sort of make out some individual stars, but for the most part, we study all of the light from different parts of the galaxy. We can look at the bulge and the spiral arms, and tell a little bit about that, each part of the galaxy and how it's different. But then you get to galaxies that are really billions of light years away, right? So 1 billion light years. That means when you observe that galaxy, that the light that you're detecting today took 1 billion years to get to you before you observed it. So these things are really, really very far away. And when you get beyond 1 billion light years to 5 billion and 10 billion light years away, these objects are so far away from us that they really just turn into dots. And then it's very hard to tell just from a picture, is it a galaxy or is it a star? And what we have to do then is take a spectrum of it. And if you take a spectrum, oftentimes you can separate it into, is it a galaxy or is it a star? Now, one other thing that's really, really neat, we like to say, and if you've been coming to Astronomy on Tap for a year now, you probably could have given this talk instead of me. But one thing you've probably heard is that telescopes can act as time machines, right? So if you see a galaxy that's 1 billion light years away, the light has taken 1 billion years to get to your telescope. So when you take that picture and analyze it, you're really seeing the galaxy as it was 1 billion years ago. So these really very distant cosmological distance galaxies are so far away, we're seeing them when the universe was only half of its current age or 1/3 of its current age. So they really tell us what the universe was like and what the conditions in the universe were like in its early days. All right, so I probably shouldn't go on too much longer, right? I said like 5 minutes, okay? Okay, I'm good. All right, so I have a couple more slides, but this is honestly probably the one I should end on. galaxies, so galaxies come in all different sizes. They're all different distances from us. And if you're the kind of person that really wants to study galaxies, you want to have a nice sample of as many galaxies as you can, so we can really get, what's the average galaxy in the universe like. And so, today it's like, we've sort of done this, but I can't tell you how excited people were when this image came out. So this image was taken the first time an image like this was taken was in 1995. So we said we want like a core sample of the universe. We want to take a picture that captures all the nearby galaxies, all the intermediate galaxies, all the distant galaxies. So the Hubble Space Telescope here, it was decided that Hubble would point at a relatively boring patch of sky for 10 days. 1 day of Hubble Space Telescope time is an incredibly precious commodity. All the astronomers in this room would give an awful lot to get 1 day of telescope time, right? So 10 days of Hubble Space Telescope time, that's almost, at least at that time, was almost unheard of. Who could get 10 days for one picture? But so 10 days of time was dedicated to looking at this kind of boring patch of sky, and this is what you got, right? So interestingly, there are some of these spots that have spikes on them. So those are stars, right? So even in this picture, there are some Milky Way stars in here. And then you can see, oh, look, here's a spiral galaxy. So this one, it turns out that this one isn't quite as close as you might think, but that has to be relatively close to us, because if it was much further away, we wouldn't be able to make out that structure. And so you can see, like, here's a spiral. There's another one that looks like maybe one of those SC spirals. And then you can see some things, well, that kind of sort of looks like one of those elliptical galaxies, just a ball of stars. But then you see they're just little teeny tiny points. Well, what are those teeny tiny points? Is that just a defect? Is it a star? Every single point of light that you see on this picture is a galaxy. Well, okay. Not that one and not that one. Every other point of light that you see on this picture is a galaxy. And so it was this picture, like up until this point, we had done a lot of work that really told us what a lot of galaxies in the universe were like. But this picture really gave us the finest data available at the time about just the average galaxies in the universe. And it was pictures like this that let us say, like if I go all the way back to my first slide, there are roughly 100 billion galaxies in the universe that are all filled with roughly 100 billion stars. So how do we know there are roughly 100 billion galaxies in the universe? Well, we pointed our telescope at a boring patch of sky, and this is how many galaxies were in that boring patch of sky. And so we counted them up, and it turns out there's about 3,000 points in this picture. And then if you said, well, how many pictures of that same sort would we have to take to cover the entire sky? And if you multiply 3,000 galaxies by that number of pictures it would take to tile the whole sky, you get an answer of about 100 billion. So that's where we came up with this answer of there being basically 100 billion galaxies in the universe. So I'm gonna end there. I'll just sort of go back to my very first point, and then I'll take some questions. So the very first point, you live in a galaxy. You live in the Milky Way. Our sun and our solar system is just one star orbiting around in the Milky Way. The Milky Way is just one of about 100 billion galaxies. There's many millions of them that are close enough to us that we can make out the details, but there's billions more that are so far away that they really just look like pinpoints of light as well. And we have to take a spectrum or otherwise gather more data about that pinpoint to tell if that pinpoint of light is a star or a galaxy. And it turns out many, many, many of them are galaxies. All right, I'm done. Thank you very much. I hope you learned a few things about galaxies. Any questions? Judy.
I had always heard that the Milky Way was a spiral galaxy, but how do we know it's a barred spiral?
So the question was, many of us have always heard that our Milky Way is a spiral galaxy. How do we know it's a barred spiral galaxy? So it turns out like I said, it's really, really hard to figure out exactly what the Milky Way is because we're inside of it, right? So what you have to do is you just have to measure along as many sight lines as you can what the stars are like in that line, in that line, in that line. Then we also, separately with different kinds of telescopes, we measure gas clouds all throughout the Milky Way. And then we make maps of the gas clouds and we make maps of where the stars are. And then we just try and interpret that. Does it look like a spiral galaxy or does it look like a barred spiral galaxy? And in certain sight lines, there are certain parts of the Milky Way where it looks very much like there's a bar. A big problem is, though, being inside the Milky Way, we can really only see the closest half to us. And so if I go all the way back to the beginning, to this picture, right picture? Yeah. Right? So here's where we are. We can measure all of this stuff pretty well. We can measure this part of the center of our galaxy pretty well. All this stuff on the other side, that's where it gets hard. You can measure the gas clouds on the other side of the Milky Way, kind of, sort of. You can't really see the stars on the other side of the galactic center. So we have to sort of infer what that half of the Milky Way looks like based on what we see from the near half. And it does look like there are stars in an elongated sort of bar shape, and so that's why we say we're pretty sure the Milky Way is a barred spiral. Other questions? Go ahead.
In the Hubble image, why do the stars appear with like a sort of cross?
That's a great question. So the question was, if I go back to that Hubble deep field image, why do the galaxy points of light look like just sort of roundish spots, but why do you have spikes on the stars? So it turns out if there was a roundish galaxy near enough, and it was unresolved, you might see spikes on that too. So if you have a true point source, that means that the telescope can't tell that there's some extension to it, that it's a small enough amount of light that it looks like a point to the telescope. The telescope has a mirror in it that's supported by these metal arms. And so when you have light from a point source coming into the telescope, some of the light will reflect off of those arms, and it gives you're basically seeing a reproduction of the support structure of the telescope. So those are fake. Like in reality, right, stars are really just points of light, but we see them appear as those spikes because of the light interacting with the support structure of the telescope. Any other questions? I thought I saw another hand. Go ahead.
Do elliptical versus spiral galaxies depict age, or is it just...
That's a great question. So the question was, is elliptical versus spiral, is that age? And that's exactly what Hubble was thinking along the lines of. He thought these were the young galaxies, the ellipticals were young, and then over time a round elliptical would stretch out, and then it would grow a disk, and then the disk would separate into spiral arms. So he thought the age went like this, youngest to oldest. And it turns out that's not right at all. So what we think today is that we see lots of examples of galaxies merging with each other. That might be something that guy right there studies, right? So if you have galaxies interacting with each other, we can see them at various stages of that interaction process, and the ones that are pretty far along, they start to look like ellipticals. So it looks like at least some of the elliptical galaxies in the universe, it goes this way, that if you take that plus that and merge them together, you might get something that looks like that. Any other questions? All right, question from Michael.
So in that Hubble deep field image that you had, have there been, there have been more deep fields that have been taken, have they been able to discover that there are actually more galaxies that we thought from this one because they're longer exposures and they can see more galaxies?
All right, so Michael's going to ask me a question where it would be helpful if I had read a paper on this in the most recent few years. So I'll tell you what I think, and then you can correct me because you've probably read a paper on it more recently than I have. So overall, so basically what we have to do is, right, we have to count the galaxies in this image, and then we just multiply that by the number of images it would take to tile the whole sky, and then we get a number for how many galaxies there are in the universe. But we know, as good as this image is, we know we're missing some galaxies. We're still only seeing some fraction of them. So you have to estimate how many of them are you missing. And so we have since this original image, we've taken the ultra deep field, and then the extreme deep field, right? So better cameras looking at the same patch of sky for longer periods of time. And my understanding is we've refined that number, but not by a huge amount. Like I think there was one paper not so long ago that said, if we're really, really careful about differentiating between the most massive galaxies and the little wimpy ones, that we're probably underestimating the total number of galaxies by maybe like a factor of a few. But I don't. Anyway, so anyone who's read a paper on this more recently than I have want to dispute that? Or are you going to be happy with that answer? Howard? No, you're good?
Close enough.
Okay.
Close enough.
All right, close enough. We're pretty good, and the numbers evolved as we've had better images, but I don't think it's changed dramatically. Ed.
What's the farthest redshift out that you've been able to see a galaxy?
Okay, so I was going to talk about redshift, and then I'm like, maybe I'll skip. So I'll do a quick. So the question was, what's the furthest redshift we've been able to see? So I should do the quick. What is redshift first? So if you take a galaxy and you move it really, really far away, you'll notice like here's a spiral galaxy, and it doesn't look blue. It looks kind of like an orange spiral galaxy. That's because that one's far enough away that some of its light has been redshifted. So if you take a galaxy really, really far away, the universe is expanding, and the way the expansion imprints itself on these galaxies is it makes them look redder than they would if they were right up close to us. And the further it is away from us, the more that its light is affected. And so for individual galaxies, it's hard to see like a plain old Milky Way-like galaxy beyond a redshift of a couple, like a redshift of 2 or 3. But there are these really amazingly bright galaxies that have supermassive black holes in their core that are generating a lot of extra light from the core, and those are called active galaxies. So active galaxies can be 100,000 times brighter than a Milky Way-like galaxy, so we can see them to further distances. So the redshift record holder among active galaxies is around 7. So when we say a redshift of 7, that means we're seeing that galaxy from when the universe was 1/8 of its current age. But then there are these explosions that go off. Inside a galaxy, you can get explosions that happen of 2 massive stars colliding, and those explosions are so bright we can actually see them even further away. So the redshift record holder for gamma ray burst is beyond that. It's Mike, what's the redshift record holder for a gamma ray burst? Is it like 10? What'd you say?
9.
9. Okay. So gamma ray bursts have been seen to like redshifts of 9. So the winner for the longest time for most distant thing had been a quasar, and then gamma ray bursts surpassed quasars. Any other last questions, or should we call it a night and think about what fun we're going to have at the next Astronomy on Tap? Cool. Well, thank you, everybody. It was a lot of fun.